Alright, thanks for watching and welcome to the ultimate analysis proof that will combine the concepts of supremum, limits, limsups, and inductive constructions. Let me ask you this, are you ready for the challenge? I can't hear you. Well, I really can't because it's YouTube, but let's assume you're ready. And it has to do with the concept of a limsup, which I want to remind you is the following. So the limsup as n goes to infinity of Sn is just the supremum of Sn, but after a long time. So if this is your sequence Sn, then the limsup is just the supremum of Sn, but after a large capital N. So it is the limit as capital N goes to infinity of those supremums. Now, this is a very abstract concept because you're taking supremums, you're taking limits, but the question is there a more concrete way of describing the limsups? And the good news is, yes, there is, because it turns out that no matter how crazy our sequence is, kind of like that, it turns out there is always a subsequence that will converge to a limsup. In other words, there's always an express train that will go to the limsup. So it's not that abstract anymore. We can actually attain this using subsequences and limits. And this is what I want to show. So theorem. If Sn, so for any sequence, not just bounded, so any sequence Sn, there is not only a subsequence, but actually a monotonic one, so non-increasing or non-decreasing, that converges to the limsup. By the way, similarly with lim-tonic. Subsequence S and K that converges to the limsup. To the limsup as n goes to infinity of Sn. Okay, and we'll prove this, and again, careful, it is a quite tricky proof, so hopefully you will survive. And before we do that, I would like to remind you of the concept of a dominant term that we talked about a couple of videos ago. So recall, we say that Sn is dominant if anything after Sn just goes downhill. So if m bigger than Sn implies Sm is smaller than Sn. So really think of it as a peak. In other words, Sn is dominant, that is, it's a peak, for instance, if and only if anything after Sn is definitely smaller than Sn. Think like investing in a stock market, but then it crashes. So anything after your investment will just go down. All right, and not only that, there's actually something interesting to notice. Well, if Sn is dominant, it's actually bigger than anything that follows. So notice, and this will be very important, if Sn is dominant, then Sn is actually the supremum of Sm, where m is greater or equal to n. So it's really the biggest value of whatever follows it. And this will be very important because this will relate dominant terms with limsups. All right, so that was the just the prep for the proof. And now let's actually do the proof. So proof, if you want, step 0 if you want. So let T be the limsup. Goes to infinity of Sn. And just for simplicity, assume T is finite, because you'll see the proof is already hard enough. So assume t is finite. But it's not a big problem, because if t is minus infinity, it means the lim sup is minus infinity. So actually the sequence just goes to minus infinity itself. And if the lim sup is infinity, then you just readapt the proofs of steps 3 and 4. So the point is, it's not a big deal. All right, and then what we want to do, again, it has to do with dominant terms. And so first of all, case 1, so if one's not the actual first step, just like the previous proof, assume there are infinitely many dominant terms. From case 1, assume there are infinitely many dominant terms. In other words, there are infinitely many peaks. I hope this piques your interest in lim sups. So there are infinitely many peaks, and it turns out those peaks are actually our sequence that converges to the lim sup. So it turns out this subsequence, let's call this, Sn1, Sn2, Sn3, if you want Snk, Snk plus 1. Turns out this subsequence converges to the lim sup. So the infinitely many dominant terms, Sn1, Sn2, So claim our subsequence Snk works. Well, there are two things we have to show. We have to show that it's decreasing and it converges to the lim sup. But that's not a huge issue, because if nk plus 1 is bigger than nk, well, notice, what does a dominant term mean? It means anything after that is less than the beginning. In particular, Snk is dominant, so anything after Snk must be smaller than it. So in particular, Snk plus 1 must be smaller than it. Then since Snk is dominant, we must have Snk plus 1 is less than Snk. Therefore, it is decreasing. And lastly, why does it converge to the lim sup? Is by the property I raised that relates dominant terms with lim sups, with supremums. Now, since Snk is dominant, we also know that Snk is the supremum of whatever follows it. Snk, it's the supremum of Sn, where n is greater or equal to nk. And it doesn't matter if you put greater or equal or strictly greater than, because in the lim sup we'll take limits. So the point is, even that will converge to the lim sup. If you really want to be picky, you can just say, oh, this is greater than nk minus 1. So if a number is greater or equal to 8, it is strictly greater than 7, which is 8 minus 1. But then what is the limit of Snk? The limit k goes to infinity of Snk. That becomes the limit as k goes to infinity of the supremum of Sn's, where n is greater or equal to nk. But here's the thing, nk goes to infinity as k goes to infinity, so really this is saying the supremum of Sn, but after a long time. And since we know that thing converges to the lim sup, the whole thing actually converges to the lim sup. So this actually equals to t, which is the lim sup. Because you see, for any capital N, this converges to the lim sup. So for this specific one, it also converges to the lim sup. All right, very good. And therefore, what have we found? We found an decreasing subsequence that converges to T. And therefore, we're done. At least for that case, where there are infinitely many dominant terms. Okay, and now let's consider the interesting case, namely where there are only finitely many dominant terms. Only finitely many dominant terms. And in particular, what this is saying, there are only finitely many peaks, if you'd like. And well, if there are only finitely many peaks, there must be one last one, right? Kind of the last dominant term. And let's call that Sn naught. Maybe something that looks like that. So let Sn naught be the last dominant term. Particular, anything after that isn't dominant anymore. And then it turns out there's something super interesting happening. Namely, if you take any capital N bigger than capital N naught, and you consider the supremum, so the biggest value of Sn after capital N, it turns out that supremum is just constant, equal to T. So that supremum doesn't depend on capital N anymore. And it seems surprising, but we can show this. In fact, let's do that. Claim if N is bigger than capital N naught, then if you consider the following supremum of Sn, where n is bigger than capital N, that equals to T. In other words, it doesn't depend on capital N anymore. And let me explain this in a little bit more detail. Remember, this was the sequence that is used to define the limsup. And we have shown, in the video on limsups that this is a decreasing sequence with limit being a limsup. But what we're saying in this case, if there are only finitely many dominant terms, this sequence not only converges to T, but actually becomes constant, equal to T. So this is what the sequence of the supremum of Sn after capital N actually looks like. And let's prove this. So proof of claim. So suppose not. Then what do we have? Well, we know this sequence is non-increasing. So again, suppose it is not eventually constant. So it looks maybe like that. It might be constant and it goes down, and it might be constant and it goes down. Then, since this sequence, supremum of Sn, where n is bigger than capital N, is non-increasing, what does that mean? If it's non-increasing and not constant, it means at some point it has to go down. In other words, there is some capital N such that if you look at the capital N plus first term, it has to be smaller than it. Then there is a capital N such that the n plus first value of this sequence is strictly smaller than the nth value of this sequence. Such that the supremum of Sn, where n is bigger than capital N plus 1, is strictly smaller than the supremum of Sn, where n is strictly greater than capital N. So again, in other words, there is a drop at capital N. So after the supremum after capital N plus 1 is strictly less than the supremum of N bigger than capital N. But just one little technicality, so this is again supremum of Sn, where N is bigger than capital N plus 1, and this is less than the supremum of Sn, where what happens? Well, if N is bigger than 8, then it's bigger than or equal to 9. So this becomes N greater or equal to capital N plus 1. So in other words, again, same idea, there is a drop at capital N plus 1. This is capital N, and this is capital N plus 1. Okay, now let me give you a little analogy. Suppose you have a group of 20 students and the highest score was 90. Now, suppose one student dropped and suddenly the highest score is 85. What does that mean? It means that student who dropped had the highest score. So any other student must have a lower score than that. In other words, what is this saying? It says that this S capital N plus 1, again, that best student must be much better than any other S cap M's in some sense. So in other words, what is this saying? This means if M is bigger than if M is bigger than capital N plus 1, then Sm must be worse. It's not the best student anymore. Must be less than S capital N plus 1. But that's a huge issue. Why is that true? Because, and why is that an issue? Because remember we said S capital N naught was the last dominant term. But this is really saying that S capital N plus 1 is a new dominant term. Because this is saying that anything after S capital N plus 1 must be strictly worse. So the point is, this implies S capital N plus 1 is dominant, and that really contradicts the definition of S capital N naught, because we said S capital N naught is the last dominant term, but we just found a new one. Contradiction with what? Contradiction with the fact that that sequence doesn't become constant. So from now on, we know that the sequence of supremums eventually stabilizes and becomes constant. All right. So now, back to case 2. So that was a lemma that was important. And I hope you're still listening, because it's going to get real exciting soon. So now let's do our third step. And now we're back to the future. So back to case 2. So what does case 2 say? We have finitely many dominant terms, and we have this amazing lemma where the supremums eventually become constant. And now, really, step 3 is the core. That's where we want to find our subsequence that's monotonic and converges to the limsup. Now, here's if you want a little subcase. Namely, suppose, and that's completely possible, that infinitely many, so again, this is the limsup, this is T. Now, it's entirely possible that infinitely many of our Sn's are equal to T. Suppose, again, infinitely many Sn are equal to T. But then we're trivially done, because just that subsequence be those infinitely many Sn's, and well, it's monotonic because it's constant, and by definition it converges to T. Then we're done. So really the interesting case is if there are only finitely many of those, or even none of them, that equal to t. So assume, so from now on, assume only finitely many Sn are equal to t, and let capital N1 be bigger than the last one that equals to t. So this is t, and again it's possible that a couple of them are equal to t, but now let's just pick capital N1 such that this isn't true anymore. So capital N1 that is bigger than, remember, capital N0, which was the last dominant term, such that if n is bigger than capital N1, then Sn is not equal to t. And in fact, we can say even more than that. In fact, we have Sn is strictly less than t. Sn is strictly less than t. And why is that true? That's because, remember, we are a stabilizing thing. So remember, we have this capital N0, and look, if, okay, suppose this is t, if some Sn were bigger than t, then the supremum of the Sns would also be bigger than t. But then that would be a contradiction, because remember, a sequence of supremums is constant. Okay, again, because if Sn were bigger than t for some n, then if you want the supremum of Sn, where n is bigger than, I don't know, capital N0 plus 1 or something, let's say bigger than capital N0 is bigger than t. Let's do it this way, okay? And then that's a contradiction, because we assume that the sequence eventually stabilizes. So it's eventually equal to t. So we can actually assume that all of them are less than t. And now we are ready to construct our subsequence. So let's construct S and K inductively. So now construct S and K inductively. Again, here's where inductive construction comes into play. In other words, goal, what do we want? We want, in this case, S and K. Well, let me just double check. Is it increasing or decreasing? It is increasing. So S and K plus 1 is bigger than S and K. And so S and K, well, we already know that's less than t. That's not a problem. But it's bigger than t minus 1 over k. Let me rewrite this. And t minus 1 over k, it's less than S and k, and it's less than 1, and less than t. So again, picture-wise, what do we want? We want an increasing sequence where for each k, S and k is trapped between t minus 1 over k and t. And then once we have that, we're actually done. So we see the light at the end of the tunnel, because S and k is increasing, and then by the squeeze theorem, we get that S and k converges to t. Then we're done. Because we found an increasing subsequence, so S and k is increasing, and with limit k goes to infinity of S and k equals to t. The good news is this last part isn't too hard. So really that stuff before with soup, that was difficult. But how do we do this? Well, notice, what is the limsup, right? I mean, it has to do with soup. So if you want the base case, so consider, first of all, again, we want S and K to be bigger than T minus 1. So consider T minus 1, which is less than T. But remember, T was also the constant value of that sequence. So, of supremums. Remember that if you take the supremum of Sn, where n is bigger than capital N naught, or let's say bigger than capital N1, just to make sure it's big enough. Okay. We know that that sequence is constant, converges to constant equal to t, and that's why this supremum is just t. And we now get a number that's smaller than the supremum. So it's like the situation where you say, you are not the best student, so there's a student that's worse than you. So this is t, this is t minus 1. So we actually know that there's an Sn1 bigger than t minus 1. So by definition of the supremum, there is Sn1 bigger than t minus 1. And then we're done, at least in this part, right? Okay, so for the induction step, suppose, what do we have? We have Sn1 less than Sn2 less than dot 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 less than Snk with Sn1 bigger than t minus 1, Sn2 bigger than t minus 1/2, up to Snk bigger than t minus 1 over k. And what we want to find a term even bigger. So want to find Snk plus 1 bigger than Snk with Snk plus 1 bigger than t minus 1 over k plus 1. So in other words, what we want to find is a term, again, bigger than the previous term, but bigger than t minus 1 over k plus 1. And how do we achieve this? Basically, using the same technique as before with the soup, except we also need to have Snk plus 1 is bigger than the previous term. So consider the following. The maximum of, first of all, the stuff that we want, t minus 1 over k plus 1, but also, I believe, so S, capital N1, S, capital N1 plus 1, maybe Sn1, up to Snk. Now here's the thing, all those terms, by definition, they're less than t. So the maximum of those finite number of terms is also less than t, which I like to remind you, it's a supremum of Sn, where n is bigger than capital N. So let's ignore this term. And therefore, by definition, there is Sn, some element Snk plus 1 with, okay, on the one hand, it's bigger than the stuff that we want, t minus 1 over k plus 1. It's also bigger than Snk. And why do we need all the other terms? Well, Snk plus 1 is bigger than all those terms, so in particular, it comes after all those terms. So it's a new term in some sense, just like we did before, and therefore, we're done really by induction. So then what we get is that Snk, so Snk is increasing, and the limit in the end, k goes to infinity, of Snk is t. which is the supremum. Ta-da!